It's kind of wild when you think about it. The universe's most violent, chaotic explosions, they also happen to be its most sensitive, most precise laboratories. It's this incredible cosmic paradox, and we're going to dive right in.
So, let's start with a really big question. Something that sounds like it's straight out of a sci-fi movie. How in the world could we ever test for the existence of extra dimensions? I mean, things we can't see, can't touch, can't perceive at all? The answer? Well, it is definitely not what you'd expect. Yep, you're seeing that right. We find the answer by looking at a dying star. The key isn't in some billion-dollar particle accelerator here on Earth, but light years away, inside the final, fiery death of a massive star. I know it sounds totally backward, right? But these incredible cosmic cataclysms, they're holding the exact clues we need.
Okay, so to make sense of all this, let's think of it like a cosmic detective story. Our crime scene is this massive stellar explosion, and the evidence we're about to collect, it could literally rewrite the fundamental laws of physics.
Here's the basic idea, and it's pretty brilliant. For all their insane chaos and destruction, we actually understand supernovas really, really well. We know how much energy they're supposed to release, and we have solid predictions for how they should behave. And that's what makes them such perfect laboratories. If we see anything at all that deviates from what we expect, well, that's a blinking signpost pointing directly to new, exciting physics.
All right, so every good detective has to know the crime scene inside and out. So let's do that. What exactly happens when a massive star finally bites the dust? Let's get into the anatomy of this stellar collapse.
Okay, so for millions and millions of years, a massive star is basically a giant fusion factory. Deep down in its core, the pressure and heat are just unimaginable, and it's constantly smashing lighter elements together to make heavier ones. Hydrogen becomes helium, helium becomes carbon, and on and on. It creates this kind of onion-like structure of different layers. And all this fusion releases a ton of energy pushing outwards, which is what keeps the star from collapsing under its own immense gravity.
But here's the catch. This cosmic furnace has a fatal flaw. The party stops at iron. See, when you try to fuse iron, it doesn't release energy anymore, it actually consumes it. So you start to get this dead, incredibly dense iron core building up in the center. And just like that, the star's main line of defense against gravity just fizzles out.
And that brings us to this really crucial tipping point in physics. It's called the Chandrasekhar Limit. Think of it as the point of no return. Once that iron core gets to be about 1.4 times the mass of our sun, that's it. The internal pressure just can't hold back the crushing force of gravity any longer.
The very second that limit is crossed, gravity wins. And it wins big, catastrophically. The iron core, which might have been the size of our entire planet, collapses in on itself in less than a single second. It shrinks down to the size of a city, and that unbelievable collapse is what triggers the massive, mind-bogglingly powerful explosion we see as a supernova.
But here's the thing. That giant, visible explosion, that's not actually our key piece of evidence. No, the real smoking gun is something totally invisible, something that shoots out from the very heart of the collapse and travels across the entire cosmos without being stopped by anything.
Okay, so this is where our whole investigation takes a really interesting turn. Get this, the light, the explosion, everything we see from a supernova, that's only 1% of its total energy. A jaw-dropping 99% of it is carried away by these tiny, almost massless particles called neutrinos.
Neutrinos are so weird because they barely interact with anything. That's why we call them ghost particles. Think about it. While the light from the explosion is trapped, bouncing around for hours inside the star, the neutrinos just zip straight out of the core at almost the speed of light. They're like perfect little messengers, carrying a pure, uncensored signal directly from the heart of the explosion. They are our primary evidence.
And look, this isn't just some abstract theory. We actually have an eyewitness. Back in 1987, a star went supernova in a nearby galaxy. And for the very first time in history, we were ready. We were actually able to catch the evidence as it arrived here on Earth.
So on February 23, 1987, this wave of neutrinos from supernova 1987A washed over the entire planet. And deep underground in Japan, the Kamiokande detector caught it. They recorded just 11 of these little ghost particles over a span of about 13 seconds. And it might not sound like much, but it was absolutely historic. It was the moment that confirmed our biggest theories about how stars die.
And this is it. This is the smoking gun. Each one of those little asterisks
marks a single neutrino that was detected from supernova 1987A. On the bottom, you have time, and on the side, you have the energy of the particle. Now, just seeing this data is incredible, but the real story, the amazing part, is what happens when we compare this to what our theories predict.
Okay, we've got our crime scene, we've got our smoking gun, and we've got our eyewitness testimony. Now, it's time for the verdict. So what can this tiny 13-second-long signal from a star hundreds of thousands of light-years away tell us about something as wild as extra dimensions?
This is where it all comes together. What we actually saw was a neutrino signal that lasted for about 13 seconds. Now, our best theories, what we call the standard model, predict exactly that, a 13-second signal. It's a perfect match. But what if those theories about large extra dimensions were true? Well, if they existed, they would have changed everything. The signal would have been cut off way shorter, after only about 5 seconds.
So why would it be shorter? Well, you can think of it like a cooling competition. Remember how 99% of the supernova's energy has to escape to cool down the core? In our standard theory, neutrinos are the only things that can do that job. But if there were extra dimensions or some other exotic particles we don't know about, they'd create new escape routes. They'd be like extra holes in a leaky bucket, siphoning off energy. They would literally be competing with the neutrinos, making the core cool down way faster and shutting off that neutrino signal way too early.
So the fact that we saw that full 13-second signal is incredibly powerful evidence. It basically tells us there aren't any other major escape routes for that energy. And this is how we constrain ideas in new physics. We can't say extra dimensions don't exist, but we can say, well, if they do exist, they have to be smaller than a certain size, because if they were any bigger, they would have messed with our signal. And we can apply that exact same logic to all sorts of other wild ideas, like particles called neutrinos from supersymmetry, or even axions, a big candidate for dark matter.
And that's really the beautiful takeaway here. I love how the researchers put it themselves. The neutrino signal from just one supernova has given us a way to learn something about possible extensions to our best model of reality. It's a powerful tool for testing ideas that are, for now, completely beyond the reach of any machine we could ever build here on Earth.
It really just goes to show you the universe is the ultimate laboratory. That signal from supernova 1987A was like a gift, right? It let us peek behind the curtain of what we thought we knew about physics. And it really makes you wonder, doesn't it? With every new supernova we see, with every new signal we catch, what other cosmic secrets are out there just waiting to be revealed?